Least privilege. Opening. The key that opened everything. There is a story that circulates in security circles with enough variations that it has become almost archetypal. A developer at a fast-growing startup is given full administrative access to the company's cloud environment on their first week. The reasoning is practical and, at the time, feels generous. The team moves fast, there is no bureaucracy around access requests, and the developer needs to provision infrastructure, deploy code, manage databases, and debug production issues. Full admin is the path of least friction. For a year and a half, it works fine. Then the developer's laptop is stolen from a coffee shop. The session token stored in their local AWS credential file is still valid. Within 4 hours, an attacker using that session has deleted the production database, terminated all running instances, and removed the backup snapshots. The blast radius of one stolen credential, one session that had not been rotated, is the entire production environment of a company that 40 employees depend on for their livelihood. When the post-incident review happens, the question everyone asks is, why did the developer have permission to delete the backups? Nobody had a good answer. Nobody had ever asked it before. The developer needed to access the database for application development. Whether they needed the ability to delete it and its recovery points had simply never been a considered question. The permission existed because removing it would have required someone to think carefully about what the developer actually needed, and that thinking had never been done. This is the core problem that the principle of least privilege is designed to solve. Not malicious insiders, not sophisticated attackers, not nation-state adversaries, though it defends against all of those too. The first and most common problem it solves is the unconsidered permission, the access that exists not because it was deliberately granted, but because limiting it would have required a deliberate decision that nobody made. Every unconsidered permission is a standing vulnerability, waiting for the moment when the account it is attached to is compromised, the employee it belongs to leaves the organization, or the service running under it is exploited. Least privilege is the discipline of making every access grant a considered decision and maintaining that discipline across the entire life cycle of every identity in the environment. Understanding that discipline, what it requires intellectually, what it demands organizationally, what it looks like when it is working and when it is failing, is what this session is entirely about. The foundation, access control, and the vocabulary of permission. Before the mechanics of least privilege can be applied, the vocabulary of access control needs to be precise. The terms authentication, authorization, and accounting are often grouped together because they are frequently implemented in the same infrastructure, but they represent distinct concepts with different security implications, and confusing them produces real mistakes. Authentication is the process of verifying that a claimed identity is genuine. When a user types a username and password, the system answers one question: is this person who they say they are? Authentication mechanisms range from something like a password or PIN, to something you have, like a hardware token or cryptographic key pair, to something you are, like a fingerprint or facial geometry. Each factor type has different attack surfaces. Passwords can be phished or leaked. Hardware tokens can be stolen but are harder to clone. Biometrics cannot be rotated once compromised, which is why they make excellent second factors but catastrophic primary secrets. Multi-factor authentication combines factor categories so that compromising one does not compromise the others. 12 failed authentications before a correct one from foreign IP is an authentication event. It is not yet an authorization event. The two things are distinct. Authorization is the process of determining what an authenticated identity is permitted to do. The question here is not who are you, but what are you allowed to do? This is where least privilege lies. An employee who has successfully authenticated to their company's systems has proven their identity. What they can actually see, modify, and delete depends entirely on what access they have been granted. And the principle of least privilege demands that the answer to that question be as narrow as the job requires, and no wider. The conceptual models for how authorization decisions are made have evolved significantly, and their differences have direct implications for how least privilege is implemented. Mandatory access control, used in high-security government and military environments, assigns security classifications to both subjects, users and processes, and objects, files and systems. Access is granted or denied by the system based on the relationship between the subject's clearance and the object's classification. The individual user cannot grant themselves access to a higher classified object. MAC is extraordinarily rigid, exactly its security value, and exactly why it is operationally difficult in commercial environments where flexibility matters. Discretionary access control is the model most familiar from everyday computing. The owner of a resource has discretion over who can access it. A user creates a document and decides whether others can read it, edit it, or share it further. That flexibility is also its vulnerability. When users make poor access decisions, sharing a sensitive folder with the entire organization because it is more convenient than managing a list, the system has no mechanism to prevent it. The data classification policy says the folder should be restricted. The DAC model says the owner decides. When those two things conflict, the owner's decision wins. Role-based access control addresses this by decoupling the access grant from the individual and tying it to an organizational role. The finance analyst role has a defined set of permissions. Every person who holds that role receives exactly those permissions. When someone moves from finance analyst to finance manager, their role changes and their permissions change accordingly. When they leave the organization, revoking their account revokes all access simultaneously because access was defined by the role rather than accumulated individually. RBAC is more operationally sustainable than DAC at scale because access decisions are made once at the role definition level rather than repeatedly for each individual. Privilege escalation represents the failure state of all three models. The condition in which a user or process obtains permissions beyond what was authorized. Vertical escalation is the more dramatic form. A standard user account gains administrator or root privileges. A vulnerability in a system service running as root that a local user can exploit to execute arbitrary commands is a vertical escalation path. Horizontal escalation is subtler and often more damaging. A user operating within their privilege level accesses resources belonging to another user at the same level. A web application that identifies users by a sequential account ID and allows any authenticated user to retrieve any account's data by changing the ID number in the URL is vulnerable to horizontal escalation. The attacker has not gained higher privileges. They have abused legitimate privilege to access resources that do not belong to them. Detecting horizontal escalation is harder than detecting vertical precisely because the actions appear authorized. The user is technically permitted to make that type of request. The problem is what they are requesting, which requires behavioral analysis rather than permission checking. The structural tension, minimum viable access against operational reality. The principle says minimum necessary access. The operational reality says that determining what is truly minimum requires work that is frequently unavailable, and that the cost of getting it wrong in the restrictive direction is also real. This tension is the central challenge of implementing least privilege in a working organization. Consider the service account. A service account is a non-human identity used by an application, a script, or an automated process to authenticate to resources it needs during its operation. Service accounts are among the most common sources of excessive privilege in enterprise environments, and the reason is straightforward. When a developer configures a new service, they need the service account to be able to do whatever the service does. Determining the exact minimal set of permissions required by the service is time-consuming and requires understanding the service's full behavior across all its code paths, including the rarely exercised ones. Granting a broader set of permissions, or, commonly, adding the service account to a high-privilege group, achieves the goal immediately. The service works. The broad permissions are forgotten. 2 years later, nobody remembers why the payroll processing service account has read access to the source code repository, and nobody is certain it is safe to remove without breaking something. The service account problem has a name, standing privilege, and it is the condition in which permissions exist continuously regardless of whether they are actively needed. Standing privilege is what makes a compromised service account immediately dangerous. The attacker who gains control of the payroll processing service account does not need to escalate privileges to become dangerous. The standing privileges of the account are the attack surface. Just-in-time access is the architectural response to this problem. Permissions are granted at the moment they are needed for the duration of the task that requires them and revoked automatically when the task completes. A database administrator who needs to perform maintenance on the production database requests access through the PAM system, is granted elevated privileges for a 2-hour window, performs the maintenance, and the elevated access expires. The standing condition is that the DBA has no production database access. The exception is the temporary elevation. This inverts the default posture from always accessible to never accessible unless specifically granted. The tension between minimum viable access and operational reality also appears in the developer access scenario. A developer who discovers a production issue at 11 o'clock on a Friday night needs to fix it before it causes customer impact. The least privileged posture says they have no standing production access. The operational reality says the customer impact is happening right now. The resolution to this tension is the break glass account, a mechanism for emergency privileged access that is designed to be used in genuine emergencies, is heavily audited, and triggers immediate notification to the security team and relevant leadership. The break glass account does not undermine least privilege. It is a controlled, documented, time-limited exception to the standing restriction, with accountability built into its design. What undermines least privilege is the same developer having standing production access because everyone decided the break glass procedure was too slow, and that convenience trumped the security posture the procedure was meant to preserve. Architecture, building access structures that hold. The architectural challenge of least privilege is building access structures that accurately reflect organizational roles at the time of deployment and remain accurate as the organization changes. Both parts of that challenge are genuinely difficult, and most least privilege failures happen not in the initial design, but in the drift between the initial design and the current reality. The onboarding process for a new IT department employee illustrates the design challenge clearly. The employee needs access to servers, to network devices, and to the ticketing system. Each of those three access grants requires a different decision, and the decisions need to be made before the employee starts rather than during the first week when requests are coming from the manager, the employee, and multiple system owners simultaneously. The server access should be determined by the employee's specific role. A junior system administrator who manages Windows endpoints has no obvious need for access to Linux application servers, and granting it, because it is easier than maintaining the distinction, creates standing privilege that is not justified by the job function. The network device access should follow the same logic. Read-only access to network monitoring is appropriate for a broader range of IT roles than the ability to modify firewall rules or routing configurations, and those two levels should map to different groups with different membership criteria. The ticketing system, the architectural discipline that makes this tractable, is predefining the roles before individuals are assigned to them. An organization that has defined an IT Windows admin role, an IT network read role, and a help desk tier 1 role with specific access grants for each can onboard a new employee by assigning the appropriate roles within a defined process. An organization that makes access decisions individually for each new hire. What does this person need? Answered ad hoc by whoever is available. Produces inconsistency, accumulates exceptions, and creates the privilege creep that audits later reveal. The PM implementation for privileged access deserves particular architectural attention because it represents the application of least privilege to the highest risk credential category. A PAM solution vaults the credentials, the actual passwords or keys for privileged accounts, in an encrypted store that the human user never sees directly. When a privilege session is needed, the user authenticates to the PAM system. The system establishes the session on their behalf using the vaulted credential, and the entire session is recorded, keystrokes, commands, and screen activity, in a tamper-resistant log. Several things happen simultaneously. The user has access to the privileged resource without ever knowing the actual credential, which means the credential cannot be written down, shared, or extracted from the session. The credential can be rotated automatically after the session ends. So each elevated session uses a credential that will not work again after it concludes. And the full session recording provides an audit trail that makes every action taken during the session attributable and reviewable. The integration between PAM and JIT access is the complete architectural expression of the principle. Access does not exist until it is requested. The request is approved through an automated or human workflow appropriate to the sensitivity of the target. The session is brokered and recorded, and the access is revoked when the session ends. The standing condition is zero privilege. Every elevated session is a deliberate, documented exception to that baseline. Microsegmentation applies the same logic at the network layer. A server that needs to receive connections on port 443 from a load balancer and make outbound connections on port 5432 to the database should be able to do exactly those two things and nothing else. Microsegmentation implements this by defining explicit allow lists of permitted communication paths at the workload level, not at the subnet level, where a broad allow rule might permit any host in the application tier to communicate with any host in the database tier, but at the individual host level, where only the specific application server can reach the specific database server. The network privilege is as narrow as the application requires. When a workload is compromised, the attacker's ability to use it as a pivot point, to scan adjacent systems, attempt lateral movement to other application servers, or probe the database for accounts they have not targeted yet, is constrained by the same microsegmentation rules. The blast radius of the compromise is bounded by the permitted network paths of the compromised workload, tools that enforce the minimum. 4 tools enforce least privilege at different layers of the environment, and each one embodies the principle in a way that reveals both its value and its operational cost. IAM platforms, whether Azure Active Directory, AWS IAM, or a similar service in another cloud or on-premises environment, are the primary mechanism through which least privilege is defined and enforced for human and non-human identities. AWS IAM in particular expresses least privilege through policy documents attached to identities. A policy is a JSON document that states which actions on which resources are permitted, and everything not explicitly permitted is implicitly denied. This architecture means that the starting condition for any new IAM identity is 0 permissions. Every capability must be explicitly granted. The cost of this model is that writing precise IAM policies is genuinely difficult. A policy that is too broad grants more than intended, and a policy that is too narrow breaks the application that depends on it. AWS provides tools to help. The IAM Access Analyzer can evaluate existing policies and identify permissions that were granted but never used, which makes the right sizing process less guesswork and more data-driven. The limitation is that IAM tools enforce the access model as designed, but they cannot detect the design errors that occur when the wrong permissions are granted from the beginning. If a developer is granted S3 full access when they only needed read access to one bucket, the IAM system enforces that broader grant faithfully. The gap is in the policy review process that should have caught the overgrant before it was applied. PAM solutions like CyberArk and BeyondTrust operationalize JIT access and session recording for privileged credentials. The vault stores credentials encrypted. The workflow engine handles request and approval processes, and the session proxy brokers and records privilege sessions. The value is the elimination of standing privileged credentials as a viable attack surface. If the credential is rotated after every use and never directly visible to the user who exercises it, there is nothing to extract from the user's laptop, no credential to phish from targeted email, and no static secret to find in a configuration file. The cost is the deployment complexity of the PAM infrastructure itself. The vaulting system, the proxy components, the integration with Active Directory and each target system, and the user experience of requesting access through a workflow rather than connecting directly. The limitation that most organizations discover after deployment is that PAM requires every privileged target to support the credential rotation mechanism. Legacy systems that cannot have their credentials rotated programmatically, old network devices with limited API support, legacy applications with hard-coded service account passwords, create exception categories that must be managed separately, and those exceptions tend to be the highest risk accounts in the environment. Containers, in the context of least privilege, enforce the principle at the process level through 2 mechanisms that are worth understanding distinctly. The first is user namespace isolation. A container process runs as a specific user inside the container, and the most important configuration decision for security is ensuring that user is not root. A container process running as root inside the container is, in many configurations, equivalent to running as root on the host. If the container's isolation is broken through a kernel vulnerability or a misconfiguration, the root process inside the container becomes a root process on the host. Containers configured to run as non-root users limit the blast radius of that escape scenario. The second mechanism is capability dropping. Linux root access is not a single all-or-nothing privilege. It is composed of dozens of individual capabilities. The ability to bind to ports below 1024 to modify network interfaces to load kernel modules. A container that needs to bind to port 80 does not need all of those capabilities. Dropping all capabilities except the ones the application requires is the container-level expression of least privilege. The process has exactly the system-level abilities it needs to function, and no others. The limitation is that both mechanisms require deliberate configuration. The default container experience, running as root with a broad default capability set, is not the least privilege posture. It is the maximum convenience posture. The security posture requires additional configuration that many development teams do not apply until someone raises the concern. Secrets management tools, HashiCorp Vault, AWS Secrets Manager, and their equivalents, enforce least privilege for credentials used by automated pipelines, applications, and services. The central principle is that secrets should not be embedded in code, configuration files, or environment variables where they are visible to anyone who can read those files. Instead, applications authenticate to the secrets manager at runtime and retrieve only the specific secret they need for the current operation. The secrets manager can enforce which application identities are permitted to retrieve which secrets, how frequently the secrets can be accessed, and whether access logging is required. In a pipeline context, this means that an automation script that needs to call a threat intelligence API does not have the API key embedded in its code. It authenticates to the secrets manager, retrieves the key for this execution, uses it, and the key is not persisted anywhere in the pipeline storage. The cost is that the application must be written to retrieve secrets dynamically rather than read them from a configuration file, which requires a code chain for applications that were not originally designed this way, and a dependency on the secrets manager being available at runtime. The limitation is that the secrets manager itself becomes a high-value target. The policy that controls which identities can access, which secrets must be as carefully maintained as the least privilege posture it is designed to enforce. A misconfigured secrets manager policy is still a misconfiguration. Implementation, the work of granting and revoking access correctly. Two implementation scenarios reveal the gap between least privilege as a principle and least privilege as an operational discipline. The first is implementing RBAC in Active Directory for a company with HR, finance, IT, and sales departments. The implementation decision that separates a durable access model from one that degrades quickly is whether the groups are built around organizational roles or around system permissions. This distinction sounds subtle and turns out to be everything. A permission-centric group structure looks like this: HR file share read-write, finance SIP access, IT server admins. Each group is named after what it allows rather than who should have it. Over time, when an employee changes roles, the question, "What should we remove?" requires someone to understand which permission groups the old role required and check whether the new role needs the same permissions. A process that requires both system knowledge and organizational knowledge simultaneously under the pressure of an employee waiting for their access to be set up correctly. Most of the time, the old permissions are not fully removed. They accumulate. A role-centric group structure looks like this: HR analyst, HR manager, finance analyst, finance controller, IT junior sysadmin, IT senior sysadmin. Each group name identifies the organizational role. The permissions associated with each group are defined by a documented access matrix that maps roles to the resources they require. When an employee changes from finance analyst to finance controller, the change is one group membership adjustment. Remove from finance analyst, add to finance controller, and all permission changes cascade correctly from the role definitions. The organizational knowledge required is simply knowing what role the employee now holds, which HR already knows. The access matrix that backs the role definitions is the governance artifact that makes this work. It is a documented statement of which systems and resources each role can access, at what permission level, and why. It is reviewed periodically. Quarterly is typical, and any deviation between the documented matrix and the actual group-to-resource permission assignments triggers a remediation. Without the access matrix, the group definitions drift from intention, and the role-centric structure becomes a permission-centric one in practice, even if the group names still look clean. The JIT implementation for database administrators adds another layer of precision. The baseline state is that no DBA has standing access to any production database. The access is requested through the PAM system, which is integrated with the ticketing system so that the DBA's elevation request references the change ticket that authorized the maintenance, approved automatically if the ticket exists and is in the appropriate state, or routed to a duty manager for approval if it arrives outside the maintenance window. The PM system grants a 2-hour session, brokers the connection so the DBA never sees the actual database credential, and records the full session. When the session expires or the DBA disconnects, the credential used for that session is rotated automatically. The non-obvious consideration in this implementation is the failure mode. What happens when the PAM system itself is unavailable? The break glass procedure must be documented, known to the DBA team, and tested at least quarterly. The break glass accounts, credentials stored in a physically secured location, such as a sealed envelope in the server room safe or a password manager accessible offline, must be tested to confirm they still work, because nothing damages trust in a procedure faster than discovering at 2 in the morning during a production outage that the break glass credential has expired and nobody noticed. The break glass access logs must be reviewed after every use to confirm that the access was legitimate and that the actions taken during the session match the stated maintenance purpose. This review is the accountability mechanism that makes the exception genuinely exceptional rather than a quietly normalized alternative to the JIT process. When privilege grows without permission, 3 diagnostic journeys. 3 failure scenarios describe the conditions under which least privilege collapses in practice, and the diagnostic process for each reveals a different dimension of how the principle needs to be maintained rather than merely deployed. The first is privilege creep at scale. An audit reveals that 30% of the user population has accumulated excessive permissions. The finding is not that anyone made a single large error. It is that a large number of small errors have accumulated over time, and the aggregate result is an access environment that does not reflect organizational roles. The diagnostic begins by segmenting the population of users with excessive permissions into categories, because the root cause differs by category and the remediation differs accordingly. The first category is role changers. Employees who move from one role to another and had new permissions added without the old permissions being removed. Pull the HR records and the Active Directory group membership history for this population. The pattern is typically visible. Group memberships were added at the date of a role change, but the previous group memberships were never removed. The root cause is a gap in the mover process. The procedure for changing roles exists, but does not include an explicit step for revoking access associated with the prior role. The fix is procedural. The mover process is updated to require role-specific removal as well as role-specific addition, and the updated process is tested against a sample of the affected population. The second category is project accumulation. Employees who were granted access to resources for a specific project and never had that access removed when the project ended. This population is harder to identify from HR records because projects do not generate HR events. They generate access requests. Pull the access request records for the affected accounts and correlate them against project records. Access grants that reference a project that has since closed and that have not been reviewed since that closure are the candidates for remediation. The root cause here is the absence of time-bounded access grants. When access was granted for the project, no expiration date or review trigger was attached. The fix is both immediate, revoking the identified stale grants, and structural, requiring that access grants associated with projects or temporary needs carry an explicit expiration date or a review trigger that fires when the project closes. The third category is exception accumulation. Users who received one-off permission grants, documented as exceptions to the standard role definitions, that were never revisited. These are often the hardest to remediate because someone in the organization originally approved the exception and may have forgotten why. The remediation requires contacting the access owner, the person responsible for the resource that the exception grants access to, and asking whether the business justification for the exception still applies. Many exceptions from 2 years ago no longer apply because the specific project they enabled has concluded or the specific need they addressed has been met another way. Revoking those exceptions is straightforward once the ownership question is answered. The structural fix is an exception register, a documented record of every access exception, including who requested it, who approved it, the stated justification, and a mandatory review date. Any exception that reaches its review date without a renewed justification is automatically revoked. The second scenario is a service account failure that appears to be a permission problem. A newly created service account cannot run a scheduled task despite being a member of the local administrators group. The scheduled task fails with access denied. The symptom points at permissions. The diagnosis is more nuanced. A brute force attack leaves a clear signature. Many authentication failures in rapid succession, often from a single source IP or a small set of related IPs, often against multiple usernames, often using password authentication rather than key-based authentication. The pattern is volume and failure before any success. A legitimate administrator login looks almost opposite. One authentication attempt, success immediately or after a small number of legitimate miskeys, key-based authentication, from an IP that appears in the administrator's prior authentication history. The stolen key scenario is the ambiguous middle case. One or a small number of authentication failures followed by success using key-based authentication from an IP that is new or inconsistent with the user's known patterns. The failure pattern suggests the attacker was trying slightly different usernames or testing whether the key worked before using it confidently. The key-based authentication removes the brute force signature. The new IP is the primary indicator. and it is the indicator that requires the analyst to compare against the user's authentication history rather than evaluating the event in isolation. The privilege angle for the analyst is what comes after the authentication question is answered. Once the analyst has concluded that this looks like a stolen key scenario, the investigation extends to what the account was capable of doing and what it actually did. The analyst pulls the user's group memberships, their role assignments, and their access history to understand the scope of what was available. They pull the commands executed during the suspicious session to understand what was actually done. The intersection of those two things, scope of capability and evidence of exercise, is the incident's blast radius, and understanding it requires the analyst to have a practical command of the access model in addition to the authentication logs. An analyst who knows how to read SSH daemon logs but does not understand the difference between a user's direct permissions and their group-inherited permissions is going to miss part of the picture. Case scenario: the developer who could delete everything. You're the head of security at a 30-person software startup. The company has been operating for 2 years, has a production application serving 60,000 users, and runs its infrastructure entirely in AWS. Until this week, 2 of the 3 founding developers held full administrator access IAM policies in the AWS account. The third had power user access. All 3 had access to the production database credentials stored in a text file in a shared engineering Slack channel, where they had been posted 18 months ago when the database was first set up. Yesterday, one of the founding developers announced they are leaving the company. The offboarding is amicable, but the security review triggered by the departure revealed the full administrator access policies, the database credentials in Slack, and a service account used by the CI/CD pipeline that also holds administrator access, because 2 years ago, it was easier to grant it broadly than to figure out exactly what the pipeline needed. The constraint is that you have 2 weeks before the developer's last day. You cannot break the CI/CD pipeline during the company's product launch next week, and the remaining founding developers are resistant to changes that might slow down their deployment pace during the launch. The work begins by separating the urgent from the important. The urgent problem is the departing developer's access. It must be revoked cleanly on their last day, with no residual standing access. Before that revocation, you need to understand every system and resource the departing developer's credentials touch, so that nothing breaks when the credentials are revoked. Pull the IAM Access Analyzer report for the administrator access policy. Because they had full admin, the answer is everything, but the Access Analyzer will show what they actually accessed in the last 90 days, which is a more useful picture. Resources that they accessed frequently are the ones where their credentials may have been used in automation or workflows that will break on revocation. Each of those must be remediated before the revocation date. The database credentials in Slack are the most immediate risk. Those credentials must be rotated today, regardless of the launch timeline. Any attacker who has ever had access to the Slack workspace, or who gains access to it in the future, has those credentials. The rotation process is a coordinated step. The new credentials are generated in AWS Secrets Manager with an access policy that permits retrieval by the specific IAM roles that legitimately need them. The application is updated to retrieve the credentials from Secrets Manager at runtime rather than reading a hard-coded value, and the Slack message containing the old credentials is deleted. The launch timeline does not grant permission to defer rotating compromised credentials. The CI/CD pipeline's administrator access is the important problem that cannot be fully resolved in 2 weeks without risking the launch. The approach is to treat it as a known, documented risk with a defined remediation timeline. The pipeline's actual permission requirements are determined by examining the CloudTrail logs for the pipeline's IAM role over the last 30 days. Every API call the pipeline made is recorded, and that list of calls defines the minimum necessary permission set. The permission policy is drafted based on that list, with specific resource ARNs where possible rather than wildcards. The new policy is tested in the staging environment against a full deployment run before it is applied to production. The testing happens during the week after launch rather than the week of launch. The documented risk acceptance, the CI/CD pipeline holds administrator access until date X, at which point it will be constrained to the minimum necessary policy, is signed by the CTO, and stored in the risk register. The remaining founders' access requires a conversation rather than a unilateral change. The goal is not to strip them of productive capability, but to replace the broad administrator access with role-specific policies that cover everything they actually need and nothing they do not. The conversation is grounded in the stolen laptop scenario. If one of their laptops is stolen tonight, and their AWS session token is still valid, what can an attacker do? With administrator access, the answer is everything, including deleting the production database and all its backups, which is exactly what the scenario in every company security horror story looks like. With a scope developer policy that excludes destructive actions on production resources, the answer is much less. The founders are not the adversaries in this conversation. The adversary is the scenario of compromised credentials, and least privilege is the defense. The break glass procedure is the assurance that makes the scope policy acceptable to the founders. When a genuine production emergency requires a level of access that the scope policy does not provide, the break glass PAM account is available. It requires two-factor authentication. It sends an immediate notification to the CTO and yourself. It records the full session, and the access automatically expires after 4 hours. The break glass account is tested during the post-launch week so that everyone knows it works before they need it at 2 in the morning. The founders know the break glass is there. That knowledge makes the standing restriction survivable rather than threatening. 6 weeks after the departing developer's last day, the access model looks materially different from where it started. The CI/CD pipeline operates on a scoped policy, verified by CloudTrail, that covers exactly what it needs. The remaining developers operate on scoped IAM policies that permit modification of staging resources and read access to production, with production modifications gated through the CI/CD pipeline and the pull request approval workflow. The production database credentials are in Secrets Manager, rotated automatically every 30 days. The break glass procedure has been tested and works. No capability that the founding team legitimately needs has been lost. The blast radius of a stolen laptop or a compromised session token has gone from delete everything to read production logs and modify staging. A scope that is survivable rather than catastrophic. Closing, the permission that nobody questioned. The principle is simple to state and genuinely difficult to maintain, and the difficulty is not technical. The technical mechanisms, IAM policies, PAM vaulting, JIT access, service account scoping, are well understood and widely available. The difficulty is organizational, and it is the same organizational difficulty that produces every form of drift. The pressure of immediate need against the discipline of long-term hygiene. Every excessive permission in an environment exists because at some point granting it was easier than questioning it. The developer who needed access to the database to fix a bug got access to the whole database instead of just the table they needed, because scoping the access would have taken 20 minutes and the bug fix was urgent. The service account that needed to read one S3 bucket got S3 full access because someone copied an existing policy without reading it. The employee who changed roles got their new access added and their old access forgotten because removing it would have required someone to think carefully about what the old role required, and that thinking was not done. The discipline of least privilege is ultimately the discipline of asking the question that is most easily skipped. Is this the minimum access that gets the job done? That question is a deliberate act in every case where it is asked. It is never the default. The default is convenience. The question is security. Build environments where that question is part of the process, embedded in the onboarding workflow, in the access request form, in the periodic review, in the promotion pipeline gate. Not as an obstacle to productivity, but as a forcing function for precision. Knowing exactly what access is required, exactly why it is required, and exactly when it should expire. That precision is not just a security property. It is an organizational property. An organization that knows exactly who has access to what and why is an organization that can respond to a compromise in minutes rather than days, because they know what was available and what was touched. The stolen laptop will happen. The credential will be phished. The insider will go rogue. The question is how much of the environment they can reach when it does. End of session. Least privilege.